As the director of the German University Liaison Office, I would like to welcome you on behalf of the office to the scientific evening, Basic Research in Nuclear and Particle Physics. Professor Ulrich Wiedner will start with a guest lecture, Basic Research in Nuclear and Particle Physics, esoteric or useful for society. And afterwards, we will have a presentation by Dr. Viesturs Veckalns, observations of colorful quark interactions at the Large Hadron Collider. But yes, before we start, I would like to thank Rotary Club Bochum for cooperation for many years. And this is also not the first time as the Rotary Club supports our events by supporting guest lectures, and also Professor Wiedner was here in Rīgā with one guest lecture for 7 years in 2012. Yes, and now he's again here, and tomorrow we will go to Vilnius with a guest lecture. Yes, and Professor Ulrich Wiedner, before he starts, I would like to introduce him to you if you haven't been to his first guest lecture for 7 years. Dr. Ulrich Wiedner has been professor of experimental physics at the University of Bochum since 2006. He conducts basic research on the topic of interaction, which is responsible for the diversity of the particle spectrum of the subatomic world. Professor Wiedner is a spokesman for the international PANDA collaboration on antiproton physics at the GSI. He also participates in the BES-3 experiment in Beijing on the study of harmonium decay. He is also a spokesman for the crystal barrel collaboration at CERN. His commitment to various projects is also reflected in his participation in Wasser Celsius and the Compass experiment at CERN and many other projects. Yes, we have honor to have Professor Wiedner here in Rīgā, and now please, the floor is yours.
Well, I must say thank you very much for the kind invitation and for your kind words. And before I start, let me ask the question, who has a physics background from the audience? Okay, so I hope that you are not too bored by my lecture, because my lecture I will explain more for the general public what basic research is about and why it's useful for society. And as well for the language, we decided that I speak in English, but the transparencies are in German. So whoever is better in German than in English can read the transparency. And if you don't know German, I will speak in English what is on the transparency. So, you know, to cover a broad audience, that is the goal of the whole thing. So, I have chosen a topic which is nowadays more and more important, because our research costs a lot of money, and it's your taxpayer money, it's my taxpayer money, and I think, you know, we should rightfully justify what we spend the money for. And so I've chosen the title Basic Research in Nuclear and Particle Physics. And if you go to the people on the street and you say nuclear and particle physics, I think 98% will say, oh my God, I have no idea about that. But I hope that I could convince you that this is a useful enterprise as well for all people in the society. So, let me just start to explain what different types of research are there generally done. You have basic research, you have applied research, and you have experimental developments. And if you go to the OECD, the Frascati manual, it defines basic research, as said here, basic research is experimental or theoretical work undertaken primarily to acquire new knowledge of the underlying functions of phenomena and observable facts without any particular application or use in view. So, therefore, clearly, nuclear and particle physics is basic science, which completely fulfills this definition. So first I will now talk about two examples about basic science, where if you ask people in school or if you ask the general public, they say, oh my God, this is not useful for me at all, because I will talk about quantum physics and I will talk about Einstein's relativity theory. And I will hope that I can convince you that those two things have quite an importance for the general public. So let me start with the quantum physics. At 1900, the general observation was, we understand physics. Physics is a dead subject. We don't need to know anything anymore, because there was Maxwell's equation which explained electricity, and there was thermodynamics which explained other fields of physics. There was only a very small problem left, and that problem was a connection with a black body. Now, what is a black body? The black body is a body which absorbs all radiation going into it. So, and you could imagine a black body like a sphere, which has a very small hole, and if there goes some light or some radiation into it, then there are reflective walls here, then it will be trapped and it won't come out. So that is very close to a black body. So it absorbs all radiation, but nothing gets out. But if you look at the physicist as it, if you turn it around, then a black body sends out radiation of all energies, of all wavelengths. So, and why am I talking about wavelengths? Well, you know the color spectrum, and the color spectrum is a very small part of the photon spectrum, what we call the photon spectrum, which goes from radio waves to FM, AM, microwaves, infrared, so heat, then UV light, then there are X-rays, and there are gamma rays. It's all the same thing. It's photons which have just a different energy. And the visible light that humans can detect nicely is part of this spectrum. Okay, so what is this black body radiation, or what is this black body good for? Well, one could see the intensity and the temperature of the color which is sent out by a black body depends on the temperature that the black body has. So here you see the temperature, which is in Kelvin. So it's not Celsius, but it's a slightly different scale. So it's a Kelvin scale. And here you see the color, and you see how the spectral distribution in terms of wavelengths is. And what is it good for? Well, astronomers use it, for example, to determine the temperature of stars. And this is the temperature of the sun, and you see one can nicely determine the temperature of the sun, which is about 6,000 degrees hot. So at 1900 there was a very small problem in the description of the spectrum, and this very small problem could only be solved, and the very small problem was that it really didn't describe very well the spectrum when it goes here to a higher wavelengths, when it goes into the direction of ultraviolet. There was no really physics description of it. And that physics description was then done by Max Planck, and he could describe it by the fact that he said the energy which is in this radiation is sent out in very tiny little packages. So he said the energy is not a continuous, but they are very small packages. And these packages cannot be cut into half. So, and these packages he called quanta, and this was the birth of the quantum physics. By the way, Max Planck in the beginning, he thought this is just a mathematical trick, these packages. He said, you know, I'm so desperate, you know, I have to find a trick and to do this. And so he introduced this quantum physics. But it was actually the birth of the quantum physics. And this was, of course, a complete revolution by looking at physics. And without quantum physics, no modern electronics would be possible. No computer would be possible. No atom physics would be possible. This here, these handies, without quantum physics, we would not be able to develop them. And it's now that in developed states, industrial states, 50% of the gross national product depends on quantum physics. Because any transistor, any electronics, any computer would be unthinkable without quantum physics. So, that was the first example. Now let me come to the other example, which has to do with Einstein's relativity theory. What you all know, and I've seen the taxi drivers using it here, and most of you will use it as well, is a GPS system. How does a GPS system work? Well, there are satellites up there whose position is very well known, and this worker here who wants to know its exact position and where he or she should go to work can determine the position by receiving signals from several satellites. And so since the position of the satellites is very known, one just have to measure the time when these signals arrive, and I can calculate then exactly the position. So we need the time. In order to get the time, we need clocks, and this clock is certainly not good enough, but we need, for example, atomic clocks, and these atomic clocks are very, very good because they have a relative accuracy. You see here 12 zeros and a 1, so 10 to the minus 13 is a relatively accuracy of these clocks. Well, this is pretty good, but actually it is not good enough to get the GPS working. We need Albert Einstein's relativity theory. Why that? Well, first of all, the satellites are moving relatively fast up there. And Einstein's relativity, the special relativity theory says if something is moving relatively fast, the time will expand. The clock is moving slower than compared to the clock who doesn't move very fast. That is one thing which one has to take into account. And then there is something which is even more difficult. That is the general relativity. And the general relativity says if a clock is closer to the Earth, which is a massive body, then it will go slower than a clock which is in some distance from a massive body. Why is that? Well, Einstein said a massive body will cause the space to curve a little bit. And if the space is curved, then you can see that the light rays might have to take a different path to follow the space. So if the light rays take a different path, they might have to take a longer path, so then the clock appears to go slower. Now GPS has an accuracy of some centimeters if you measure a few minutes. So in order to achieve that, the clocks have to be accurate to 20 to 30 nanoseconds. That is 0 and then 0, and then 7 zeros, 2 seconds. So now come the corrections due to relativity. The satellites are moving fast, so special relativity applies, and that means the clock is about 7 microseconds slower. And then comes the general relativity, due to that the Earth is a massive body which curves the space, and that makes it 45 microseconds slower. So if you look at the relative difference, then it's 38 microseconds, and compare this to the 20 or 30 nanoseconds, which is a factor of 1,000 smaller. So that means which is required, and this is due to the relativity, the error that comes. That means after 2 minutes already the position will be wrong, and if we wait for 1 day, the accuracy would only be 10 kilometers, and it would be a useless system. But because Einstein has delivered the formulas how to calculate that, you can put it into the satellites and correct for it, and therefore the accuracy of the GPS system is useful for mankind. Who would have thought that Einstein's general relativity is useful for our everyday life? I think that's really very good. Okay, so the correction is going to build into the electronics of the clocks. Okay, these were 2 examples, but when we talk about basic science, we have to say that basic science has no business plan. That means because of how basic science is done, it can't be financed out by itself because it won't produce any goods that you can sell. Therefore, it has to be financed by the states and by societies. And in Germany, it's the ministries, or what is called the German Science Foundation, DFG, which funds this. Very important is that basic science, the decision if some basic science is funded, should not be taken with the fact, oh, there might be a future application coming out of that. Nobody can predict that. Because, you know, when Einstein or Max Planck did their theories, Max Planck didn't have in mind that there will be a transistor developed or a computer developed on that, and Einstein had no idea about a GPS system. So, therefore, basic science should be funded independently of that. Sometimes, the value of a basic science proposal is not recognized immediately. Like, for example, Heinrich Hertz, who was working on the electromagnetic waves that we now use in our telephones or whatever, and he put in an application to the Prussian Academy of Science to get some funding. Okay, he got it, but then there was a remark done. This will, you know, electromagnetic waves will have never ever a practical application. Well, we have radios, we have TVs, we have phones, so nobody could imagine this at the time, so therefore this remark was there. So this example says that one can't put strong criteria on which science to fund. And one has to really trust that the scientists have a good indication, a good nose for what might be interesting. And so therefore, somehow this makes the whole process of the decision if something is funded or not somehow human again. There could be some error in it. Humans sometimes are right, sometimes we make mistakes, we have some errors, but it makes it much more human, the whole process. So, and the question is, would a transistor have been developed, or solid state theory, without the trust that there is that basic science is good? Would have been the ignition for cars being developed, which makes the engines running? No, but it was actually Faraday, years before there were any cars, who studied the ignition. So, and the induction. Would have computers been developed from people who thought, oh, I need a computer? No, nobody was thinking about it. Actually, it was nuclear physicists who needed the computer to do counting experiments, for their counting experiments. So this is how they got developed. So, in generally, physics has the aim to give a description of matter and the interactions of matter from the smallest space we know. These are the particles we can study in our accelerator. It's 10 to the minus 18 meter to the size of the visible universe. So this is a huge goal, and physics would like to give a general description of that. And we have already some pretty good idea about how our universe developed out of the Big Bang. And here you see a time scale. We are here something like 13 or 14 billion years. And there was the Big Bang in the beginning, and then there are particles. And what we would like to do, how is the universe, how did it develop, what are the ingredients of the universe, and what are the forces in there. And I think for particle physics, the following sentence describes it pretty well. The dimension of particle physics might be hidden for the naked eye, but nevertheless they bear the secrets and the understanding of our world. Particle physicists would like to answer the unsolved questions of our existence. What are the ingredients of the universe? What is it made of? How did it evolve? And how does it function? And that we do, and you will hear in a later talk probably about that as well, from CERN. What one does is actually one collides particles and produces new particles, just like how it was produced in the Big Bang in the beginning. And then one studies what is happening here, what are the forces. And what is used here is again Albert Einstein, but not with his general relativity, but with his most famous formula, which says E is equal mc squared. Energy and matter are the same. So here we have very high energetic particles. We shoot them onto each other. And then we produce matter out of this energy. And this matter could be the matter which was there in the beginning of the universe. You will hear about quarks in the talk coming after me. So that is what we are doing, and we are doing it by using huge detectors. This is the Atlas detector, and here you see there you see the reference person. So this detector has a diameter of 25 meters, a length of 46 meters, and it weighs 7,000 tons. Let me ask you a question. Do you think this is a heavy detector, or is this a light detector?
Pretty light.
Pretty light, you are absolutely right, because if the detector is so big, if you put plastic foil about it, which is watertight, and you throw it into the ocean, it swims on the ocean, even though it weighs 7,000 tons. This is the other detector you will hear about in the other talk, so I will not go into that, but just give you some pictures, some impression of the pictures. This is the CMS detector, and this is the Atlas detector, and you see how huge it is. There is a technician, and here are part of the detector. So, if a particle in such collision is produced in such a collision, then it's mostly unstable and it decays, and it's living only very shortly. Nevertheless, we could reconstruct those particles which existed shortly after the Big Bang if we can look at the decay particles and we reconstruct them. So we have to measure the energy of the decay particles, and then we know, for example, the mass, E is equal mc squared. And how do we do that? For example, it might decay into photons, into gamma rays. How do we measure gamma rays? Well, gamma rays we can measure because if they are coming onto a crystal, then they produce light, visible light, and this light we can detect in a photodetector, and the photodetector makes then a voltage out of it, an electrical current. This is just like, you know, the older ones might still remember, in old times when you do photography, you had a kind of a light measuring device so that you could adjust it on your camera. Nowadays the cameras do this all automatically. But this is exactly what is happening here. You know, you transmit the light into electrical current. When you have electrical current, you can measure how big it is. So these crystals, and here are some crystals that we use in modern experiments. They are made actually this is very interesting material. This is lead tungstate. So it's 96% lead and tungsten, but because it's an oxide, it's transparent like glass, but very, very heavy. And then there are the photodetectors you can see here. And that they are transparent like glass, you can see here in those pictures where I'm looking through this detector. And this detector was essential in determining the Higgs particle at CERN, which you might have heard about it, because here you see the mass created by two photons. If the two photons had just randomly created mass, you would have seen the curve which is here, which is shown here in green. But you see that there is a number of particles where the two photons have exactly the same energy. And that comes from the Higgs particle decaying into two photons. So again, energy and mass are equivalent. So if they have the same energy, then there is a particle of this mass, and this was a Higgs particle of 125 GeV. Let me come to another example. When an electron and a positron come together, then we have matter and we have antimatter, and then they annihilate into two photons, and then the two photons go back to each other, 180 degrees, and they both have exactly half of the energy of the electron-positron pair. So here we do the opposite of energy to matter. We do matter, electron and positron annihilate into energy, and the energy comes out into photons. And the process I've described here is extremely useful nowadays in medical applications. In the positron emitter tomography or PET, what one does is one injects into a body radioactive material which sends out positrons. And then you put it, for example, to a sugar, into a sugary liquid, and then the metabolism of the body transports it to the individual cells that use a lot of sugar. Then inside there, you have then in those cells, the positron comes together with an electron, sends out the two protons. So you can study where is this liquid going. And then, you know what happens. The positron, the electron, they annihilate, the two photons coming out, and you can reconstruct where it comes from. You just need a detector which is good for photons. And if you remember, I've shown you from particle physics our crystals, which can detect photons very well. So such crystals are used in the medical application, and then we have some electronic which tells you there were two photons which were going back to back and which have the right energy, and you can reconstruct the picture. So what we have is the gamma calorimeter in particle physics, and you see this is a gamma detector for medical application, for positron emitter tomography. So the challenges are the same in particle physics and in medical applications. You need new materials, you need very compact objects, you want to build a small detector, and you have to have the electronics have to be very stable, and you have to collect the proper events. So, and if you do that, then you, for example, can see that. That is a scan which is a normal brain, how it's working. And this is a brain where you have a PET scan where there is Alzheimer's disease. And you see there is quite a number of dead regions inside the brain. So you can detect Alzheimer's disease by this PET. But the positron emitter tomography would be impossible if you wouldn't have the detectors for particle physics. If somebody has cancer, then you can treat it by radiation. And the ideal way is that 100% of the damaging dosage goes into the tumor and 0% into the healthy tissue. So, in order to achieve or to come close to this goal, you need well-focused beams and you need a good definition of the tumor volume. And therefore, it turns out, if you use electrons and photons, and you see, and here is your tumor inside the body. It has a depth of some, let's say, 15 centimeters inside your body, so 150 millimeters. And then you see that the healthy tissue on top gets, with photons and electrons, a higher dosage than the tumor itself. But if you choose other particles, like carbons or protons, then the tumor gets the most damaging dosage. This is a dosage. And you can adjust the depth, how the beam goes into the body, by choosing the energy of the protons and the carbons, carbon ions. And these were studies which were done for nuclear physicists. What is the depth of beams in certain materials? And they realized that the dosage curve of those would be like that. And then, just to show you, this, if you would use, here is a tumor, again a brain tumor, and this is a region where you would like to have the most dosage applied to. And then you see, if you take gamma radiation, then this part of the brain gets the most radiation, and here we get much less. But if you take protons, then the most goes into, you can adjust it, that it goes directly into the tumor. And then, if you would like to treat, for example, this tumor, which is very close to sensitive organs, then you need exact planning, and so you need simulations. And for particle physics experiments, we do the simulations beforehand, before we plan to do an experiment. And these simulations are actually very, very useful for the planning of a treatment. So this was what was simulated, and then you see the treatment pretty much fulfills what was required. And so the tumor could be treated and the healthy tissue could be served. And actually, this is a picture of a wasp or hornis. And so if you have a modern particle detector chip, then it counts the number of gammas, the number of photons coming out. So PET puts up the tumor, but there is as well single photons coming out, and you could even see the movement of the organs of this insect. And you can do many hundred pictures per second with modern electronics, which was developed for particle physics experiments. Because what we do is here, you know, this is an event which comes from the LHC detector, and you see there are many, many particles, and there's lots of background. So we develop simulation packages, computer programs, which can do this, which then turns out to be exactly useful for medical physics. And that there is a lot of background here. You can see for the discovery of the Higgs, you need 1 billion, you have proton-proton collisions in this collider, 1 billion per second. But only after 5 seconds, so 5 billion events, you get 1 Higgs particle. So you have to detect 1 particle out of 5 billion. So you have to be pretty damn good and know what you're doing. And here you see now a picture how it looks like. It's at CERN, and you see there are the rings and there are the beams colliding. So one starts with an accelerator, and then the particles collide in this particle physics detector, and they collide with a rate of 1 billion per second. And there are lots of events coming out, and all these events have to be handled. And in order to handle them, one needs electronics and computers. So you have to measure something. So, how can we measure something? Let's start with something very simple. You want to measure a temperature. So temperature, there is, for example, a resistive element, and the resistance depend on the temperature. And so you set up a little bit of electronics, and you measure some voltage which is proportional to the temperature. Very easy. This is how things work for temperature measurements. And if you would like to do that, you connect it to a computer and you record it. Now, let's assume you want to measure 16 detectors, the temperature. You want to measure 16 temperatures. Okay, no problem. You reproduce it, and you buy, for example, a 4x4 USB hub, which is cheap. You do some adaptations of your computer program, and you measure 16 temperatures. Well, now imagine you want to measure 160 temperatures. Well, it's getting a bit messy now. And even if you assume for a moment that you would buy 160 volt meters and 40 USB hubs, then it's already the cabling becomes such a mess that you might not want to do that. So therefore, a better system would be, for example, if one takes a multi-port voltmeter. Let's say you take a voltmeter which has 16 different entrances, and then you put it into some frame, which is called a crate. And the crate should give the mechanical stability. It should give the current, the electricity for these multi-port voltmeters, and it should have a connection for the data to flow. And such standards for such a DAQ system is VME or CAMAC or something like that, and it looks like this. Looks like the 160 sensors, much better than the 160 voltmeters, but because we have a multi-port system. And then I said it's going to being put in a crate, and the crate has certain data lines, and there are the individual devices which measure it. And there's one master device, and there are some slave devices, and the master tells to the slave which one it wants to talk to and which one can send data, and then you can send it with a few data lines which are standardized. You can send it to the computer. And nowadays the airplanes, if you don't fly a Boeing 737, is controlled by computer. So it's fly-by-wire. The computer tells the electronic, a little motor, that the flaps in the back should be moved this way. Why did I say the 737? Because the 737, where there are some problems, is still mechanical. It's still that you have a mechanical movement of the flaps. Because the original development is 40 years ago. But why I'm talking about airplanes? Well, when they first introduced the computer-controlled steering of airplanes, they realized that there was no standard in the world how to connect measuring devices and electronics to computers, except the one which was developed by particle physicists or by nuclear physicists, which was the bus standard CAMAC in the beginning. So this was the beginning of these bus systems for data treatment. So these buses, you know, the USB bus, you know, from your computer, and there are other ones as well. Okay, but now we come to the big detectors in particle physics, and these big detectors have problems of their own. You see, they are very big. For example, you need for all the detectors to get the currents there. And you see what a mess already the cables are. So one has to think about new solutions. One has to think about how to cool this very densely packed electronics, how one can make it energy conserving, and how one can cool it. You know, electronics has to be cooled, otherwise it dies. Then it has to be radiation. Radiation should not damage it. And one needs to read out big amounts of data. And how big the data are there, I want to show you. This is a DSL. If you have a DSL telephone line at home, 16,000. Then this is a gigabit network. And this is our reference, 1 gigabit per second. This is what SSD solid-state disks are. They are a few gigabytes. Then this is what the C cable between Europe and the US can transfer. You see, it's something. This is a logarithmic scale, so it's probably 2,000 gigabits per second. This was the whole traffic in the internet 2017, something like 4,000 or 5,000 gigabits per second. And these are the data coming from the big experiments. So you see, there's a complete new world opening up that one has to deal with this. And just to show you how one solves the problem to do this, solving this problem is that you make networks, and you give each of the network points a very specific address. Just like, for example, your telephone number at home. Your telephone number at home is unique in the world. And so do you do it with such networks. And then, for example, these networks talk to each other. For example, here the computer 2 sends data to 1 and 4, while 3 and 5 are independently exchanging data. And this is how you can manage such huge data loads, by such switching networks. And when you're working with the internet, then you're using the Ethernet, and it has some protocol, and this exactly goes the same way how I just showed you with the different computers, that they are individual network addresses which talk to each other. Okay. I'm getting close to the end of my talk. Not only the products of the basic research, some of the products go into applications, one never can predict it, but also the methods. And there, where basic science comes close to applied science, there's usually a huge transfer of knowledge. And out of theoretical discoveries becomes then practical applications, and out of hypothesis becomes knowledge. And you know, the World Wide Web was actually developed for as a communication tool for particle physicists at CERN, that they could communicate to each other what they have done. This is Tim Berners-Lee, who did it at CERN, and this is actually the next computer that Steve Jobs did at the time. And I knew the group very well because I was at the same time at CERN, and you know, I was partly working on this next computer. This was a next cube as well. This was one of the most beautiful computers that I like. And there they developed the World Wide Web out of that. The only mistake that particle physicists did, we should have requested for each click, we would like to have 1/100th of a cent. Then we would have no problems in financing basic science. But now, and you know that the World Wide Web is really a revolution in the world, and this shows the internet users in the world by regions from this March, and you see 50% is actually done in Asia, then Europe, it's really big. And nowadays we have in total it's 4 billion internet users in March 25, 2019. So it's really big. So I hope that I somehow convinced you that basic science is the basis of technological developments, and for industry it means new ideas and new technological opportunities. But as well, what is on the same order for our societies, that we have very well educated research personnel and human capital. And human capital, this is somehow an output which we produce continuously in nuclear and particle physics in the academic sector. And here you see, for example, the Atlas collaboration, which actually is 3,000 people. This is the author list of the paper where they discovered the Higgs. And you see 3,000 physicists from all over the world working together to put this big detector there and to do this discovery of the Higgs particle. So I think this was not only a physics experiment, this was also a sociological experiment. Would it be possible that people from Russia, from China, from Brazil, from Mexico, from Europe work together, produce individual parts of these very challenging detectors, and it was put together and it works? I think this is a fantastic experiment that humans did there. And so, to wrap up, basic science is motivated by curiosity. We are curious, we want to find out something. Applied science is addressing very specific questions. So therefore we say, if it's successful, basic science leads to revolutions. And I showed you quantum physics, I showed you Einstein's relativity theory. Successful applied science needs to evolution of a product. And now I do a quote from Antoine de Saint-Exupéry. You know him from The Little Prince. And he said, if you would like to build a ship, then don't collect people and tell them to get wood and put them to work, to specific works. But that would not work so well. But tell them about the desire of the wide open sea, to explore the wide open sea. And I think that is what we are doing with basic science, you know. We ask the humans for the desire to discover something. But this is particle physics, people where they go, and even though they are trained in something which has nothing to do a priori with normal life, but they are trained in very different fields. So 13% go to banks and insurances, 4% go to, for example, consulting companies, 23% go to research and development in industry, 35% do communication and IT, 7% are independent, 10% stay at universities and schools, and 8% remain in particle physics. So in general, basic science makes the humans to a thinking human, who would like to understand the role of humans in the world. We would like to know where we come from. We would like to know where we go to. And therefore, it is part of the cultural heritage of humans to be curious, to would like to find out what it is. And this makes us humans, and it belongs to humanity just like art, language, tradition, and music. And with that, I would like to thank you very much for your attention. And I can take any questions that you have. I'm not sure if I can answer all these questions, but I can take them. Thank you very much.
Thank you very much for your very interesting guest lecture, Professor Vīdner. Yes, and now you have time for questions or maybe some comments from your side. Yes, please.
I have one question about this slide with the Rīgā.
Yeah.
It was quite surprisingly so that just some percent stay in technology.
Yeah.
In languages. But the question is, this is for bachelor, master, or doctoral degrees?
This is for basically bachelor degrees. Do not exist. People go on to the master. Then it's master and doctorate degrees. Yeah. Yes. Other question?
No questions in the moment? Okay, so I would like to thank them in this moment. Thank you very much, Professor.
Oh, thank you so much.
Christmas is coming.
And thank you so much for having me here. It is really a pleasure to be here and to have such an attentive audience of people listening. Thank you very much.
Yes, so now I would like to move to the second part of our event. And yes, in April 2012, Viesturs Veckalns participated in the guest lecture of Professor Vīdner, and after his guest lecture, Viesturs Veckalns got so inspired that in the autumn 2012 he started his PhD studies. So I'm really glad that we could organize such an inspiring lecture. And Viesturs Veckalns obtained his doctoral degree in 2019 at Rīgas Tehniskā University. And since 2015, he's a researcher at the CMS experiment of CERN Large Hadron Collider. And now the floor is yours.
Thank you. I will talk about quark interactions. I am the one who has practical experience in doing elementary particle research, and it's based on my thesis. And you can also free to take these materials if you would like to, and read more about it. I will talk about the ways quarks interact, not through the electrical charges they also have, but through the color charges they have. And first of all, what is a quark? The atoms consist of nucleons, the protons and neutrons, but the protons and neutrons still have constituents, and these are called the quarks. For example, the proton consists of two u quarks and one d quark, and the neutron is just the opposite. And if you sum the electrical charge of these quarks together, then you get that the proton has 1 unit of elementary charge, while the neutron is completely neutral. In total, there are 9 quarks. We think there are no more, just 9, and they come in 3 generations. First generation here, this is overall stable. You see stable here. It doesn't disappear. As I said, our world is composed of the u and d quarks. Like the proton consists of 2 u quarks, 1 d quark, and also the electron, and also there is the anti u quark, anti d quark. Everything you can also have anti, but this is not really part of our world. You can have also the anti feature here, and then we can have somewhat more excited world. This is his second generation, and we still experience some of the second generation, the more excited one, also in our lives. For example, we are continuously bombarded by the muons coming from space. So the muon is a more excited version of the electron. And then you can also have an extremely excited world, that's the third generation. And this third generation could be present at the time of the Big Bang, but now our universe is extremely cold, and you need big accelerators like the LHC to generate the third generation particles. We are very familiar with the electrical dipole. If you have plus and minus charge, then we can draw the electrical field lines like this. But you can also have another type of charge, which is called the color charge. And colors come in three varieties, and we can call them red, green, and blue. And the quarks carry the color charge. And just as an electrical dipole, we can construct the color dipole. And just as there is the electromagnetic field, we have the color field. It has its own physical properties, but it's somewhat similar, but not completely, to electromagnetic field. We can also construct electrical tripoles, if you would like to call those. So the proton and neutron, we could call them tripoles. And the term color was coined by a physicist, Wiener, in 1964. And the term color somewhat reflects the doubt if we can really take the model seriously. That's why quarks have also funny names like the bottom quark, the strange quark. People, when they coined these names, they still had a lot of doubt if what they are thinking is really true. So how do we make the color dipoles in order to start with? In order to make color dipole, we need to have a lot of energy, a high density of energy, so that we can use the Einstein's equation to create from the energy particles. One way is to construct the accelerators, and the Large Hadron Collider is just one of such accelerators in the world, but it's different from other accelerators because it has a very high center of mass energy. So we can produce the Higgs boson and very heavy quarks in large amounts. The LHC is underground, and we have experimental insertions that you see, the Atlas, CMS, where we actually make the collision. And the LHC is a proton-proton collider. You can have also other colliders, proton, antiproton, or electron-positron colliders, all types of also heavy ion colliders. This is how the LHC looks like from the inside. So you see the dipoles, and the protons are circulating in two opposite directions inside the tubes. So, as the LHC, we make a proton-proton collision with a very high energy, and from this high energy we create quite heavy particles that we study. Now, one type of particles that we are interested in, and only the LHC is very good at it, is the top quark. In the past, also Fermi was producing top quarks, but now it's closed. So we produce the top quark, and the top quark is a third generation quark. So you really need very powerful accelerators. sun is too cold to produce top quark. It is speculated that in the space two very energetic particles collide, they could also produce top quark. But in order to produce it in large quantities, we need accelerators. But it was obviously present in the early stages of the university when it was very hot. And also, the top quark is the heaviest particle that we know of. It's even heavier than the Higgs particle, which is the second heaviest particle. And the top quark was discovered in 1995 at Fermi. So, the top quark decays via the weak decay. The weak decay we experience in the decay of radioisotopes, for example, in the medical applications. And the top quark also decays in the weak way. It emits a weak quark, which is another very heavy quark, and the weak boson. And the weak boson is a heavy version of the photon. And the weak boson could decay in two quarks. And the quarks don't exist as separate identities as the electron, for example, because nature doesn't allow colorful objects to exist alone. So we see quarks as not as individual quarks, but as jets of particles that happens through the hadronization process. And if quarks are color connected, then we see that the particles are dispersed in some peculiar ways that we would like to study with our detector. So, how does the hadronization take place? So, we have two very energetic quarks that are connected in color. So, these quarks have a lot of kinematical energy and they try to separate. The color lines act like springs that try to keep them together because nature doesn't allow to exist, doesn't allow colorful objects to exist alone. As the quarks separate, the kinetic energy starts to get pumped into the color field. And when such a lot of kinetical energy is pumped into the color field, the color lines start to break apart. But instead of creating two separate colorful objects, two new quarks are created, which are in turn connected in color. So we can continue this process until we get somewhat stable pions or stable protons and neutrons. And we study this hadronization products with detectors like the CMS, that's the LHC. So we have the beam pipe and we collide the protons inside the detector, and then the particles come from the interaction point through different layers, like an onion, and each layer is meant to study certain kinds of particles. So we see the detector in real life. There are humans doing some repair, so we see that it's a big machine. And there are many layers of the detector. In the center there is the tracker that identifies and the trajectories of charged particles. Then we have the calorimeters for measuring the energy of charged particles and photons, and the hadron collider for the neutral particles, and also for the charged particles of it, and the muon chambers. And in total we have a lot of proton-proton collisions, and only a few of them make top quark and top anti-quark pairs. And still from that huge amount of top quark and top anti-quark pairs, we select events that are interesting for us from the polarity and kinematic requirements. So out of that huge amount of collisions, we get down to a very small number of interesting events. And we do statistical analysis of the data. We use a lot of computer modeling, and we identify observables and make this kind of plots for our studies. So that's all for me.
Thank you for Viesturs Veckalns for your presentation. Do you have any questions now, or maybe comments? Yes, please.
What exactly is it that you do? Probably this plot, and could you explain?
I work as a physicist at the top quark physics group. There are many studies at the top quark physics area, and I'm doing just this particular study.
And what can we see in this plot?
Yes, as I said, when the quarks are color connected, if the quark wouldn't be color connected, we would see they hadronized, but the hadronization products are distributed isotropically. But if they are color connected, we see we see that the distribution is no longer isotropical, but there is something interesting happening in the space between the two quark jets. We develop observables and study the distribution of the decay products and compare them to models where the quarks aren't color connected.
And then the plot was kind of rolled open. The detector kind of rolled open, probably, right?
The plot is shows a pull from one quark jet to the other, which basically means that there are these particles that are marked in red instead of this. We have this. That is what's shown by the plot.
Okay.
Some other questions or comments?
Maybe still a question. Can you show the next slide, please? Can you describe to one more time to non-physicists what type of what type of forces you are putting on this pair? What you are doing with this pair?
That is a color dipole. So the two balls are two quarks.
Mm-hmm.
And this is the same pair that you see here. So these two quarks, see that?
Mm-hmm. The red one, yeah?
No.
This big one, okay.
These two quarks.
Yeah, this level, yeah.
This is a color dipole.
Mm-hmm.
And it hadronizes. It hadronizes by creating new particles. That are shown here.
Maybe can you describe what does it mean, hadronization?
Yes. it means that from two quarks we create, instead of having separate quarks like electrons, for example, we have other particles that are composed of quarks.
But no, this is a representation, this is the result. But what you are doing with these quarks, what is, you are putting some forces, additional electricity, magnetic field, what you are doing?
The quarks have a very high energy, and we allow this energy to be converted to new particles.
Just by waiting?
Yes.
So no additional influence or force?
No, that's a natural process for them to atomize.
Can you show the next slide? You're showing that you force something, so you force, or it's just time is going and additional pairs appear?
So you have a lot of energy that starts from the collision and then from the decay of the top quark. So they have a lot of energy, kinetic energy.
So if you obtain a bigger number, so this is beginning pair.
Yes.
Then if you obtain a bigger number of pairs, then some energy of pairs of every pair should be lower. Yes?
Yes, exactly. Until it goes to some ground level where this process stops.
Another questions? If not in the moment, or
Maybe one short comment about these interesting events. What is interesting exactly? Could you some words say?
First of all, the quality requirements. So we identify leptons in the decay, but we want to be completely sure that it's a lepton, so we impose quality constraints. Also, we would like to have certain decay modes. We are not interested in a top quark that decays to 2 leptons. We want top quark to decay to a color dipole. So we just select the color dipole decay mode and discard the electronic decay mode. That's it.
thank you very much for your contribution today. I would like also to thank you all for participation tonight. This was the last scientific event in this year, 2019 in Rīgā. But the next week we will have our traditional Christmas concert. So you all are invited to come together with your families and friends. And this time we will have something different. We will have jazz music. And now we can continue our discussions with some glass of wine outside the room. Thank you very much for your